Hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. Topic is Chemical Machining Problems and Solutions. Okay, right. At the end of this session, student will be able to solve the problems on material removal rate of chemical machining. Okay, so this is the course learning outcome of the topic. Right. However, here students can be able to find the other parameters. The material removal rate is also given. Okay, usually, some known values will be given in the problem. We need to find one unknown. Okay. So don't think that every time we need to find the material removal rate. Okay, right. So in usual manner, let us discuss the various non-traditional machining processes. Okay. So non-traditional machining processes have classified basically into mechanical, thermal, chemical and electrochemical. Okay. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Okay. In thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. In chemical and electrochemical, chemical machining, photochemical machining, electrochemical machining. Now we are discussing the problems and solutions of this chemical machining. Okay, right. Now let us look at the problem number 1, material removal rate calculation. Okay, now let us first look at the problem. A plasma beam with a power of 500 watts is used to machine a steel workpiece. Okay. The specific energy required to remove the material is 2.5 joules per cubic millimeters. Calculate the material removal rate in mm cube per minute. Okay, right. So here the power is given. Okay, 500 watts. Okay, so if it is given in kilojoules per second, we have to convert into joules per second. If it is given in watts, just convert it to, keep as it is 500 watts, nothing but 500 joules per second. Okay, so if it is given in kilowatts, we have to multiply with 1000. Okay, it is not given, no issue. Okay, so usually we have to check these units. Okay, right. Specific energy is given, ES, that is 2.5 joules per mm cube. Okay, now calculate the material removal rate. Okay, right. So basically we have formula to find the power. Okay, the formula is that material removal rate into, what is that one? Specific energy. Okay, this is the basic formula. But here we need to find the material removal rate. Okay, so power is given, that is known value, and this specific energy is also given, that is also known value. Okay, now we have to find this one. Problem number 2, heat affected zone with calculation. Okay, right. In a plasma beam machining process, the thermal diffusivity of the material is 1.5 meters into 10 power minus 5 square meters per second. And the beam exposure time is 2 seconds. Calculate the width of the heat affected zone. Okay, so here we need to find the width of the heat affected zone. Right. Thermal diffusivity is given. Okay, that is alpha. Exposure time is given. How much? It is 2 seconds. Okay, given. Now calculate the heat affected zone. Here we have the basic formula to find the heat affected zone is that square root of 4 alpha T, where alpha equal to thermal diffusivity and T is the exposure time. Okay, beam exposure time in seconds. Okay, right. So however, the formula has written some little modified. If this 4 comes out, then it is 2 4 alpha T. Okay, so no issue, whatever it may be, the same answer. Okay, so substitute the values alpha and T. So we get this value 11 mm. Okay, right. Next, problem number 3, power density calculation. Okay, a plasma beam has a diameter of 2 mm and delivers a power of 1 kilowatt. See, already just we have discussed that in the earlier problem. The power is given in watts, but here the power is given in kilowatts. So we have to convert that one into watts. Okay, so calculate the power density in watts per in mm square. Okay, so 1 kilowatt equal to 1 into 10 power 3 watts. Okay, so 1000 watts. Okay, right. Now here we have a basic formula. Power equal to power density into area. Okay, so here power is given and area is given. Okay, sorry, what is given? Power is given. Calculate the power density. Yeah, diameter is given, area is not given, so we have to find the area. So area equal to this one, pi r square or pi into d by 2 square. Okay, so that we get the area of the beam. Okay, once if we get the area of the beam, okay, so the unknown value power density that we can calculate. Okay, calculate the power density. Okay, so in watts per mm square. Okay, required unit is given. So here power is given in kilowatts, so we have to convert into watts. Okay, right. Problem number 4, plasma beam spot size calculation. Right. If the plasma beam has divergence angle okay of 0.2 radians and is focused on a workpiece located 60 centimeters away from the plasma source, calculate the spot size on the workpiece in millimeters. Okay, so here divergence angle is given, distance is given, and spot size T is to be calculated. Okay, so it's very simple. Okay, the formula is 2 times d into tan theta by 2. Okay, so substitute the values so that we will get 120 mm. Okay, right. Next, temperature rise calculation. Okay, during plasma machining, a material with a specific heat capacity is given, and a mass of 200 grams that is given, absorbs 10 kilojoules of energy. Okay. Calculate the temperature rise in the material. Okay. So we have basic formula Q equal to M Cp delta T. Okay, where delta T is the temperature rise. Okay, so we need to calculate this one. So here Q is given, M is given, Cp is also given. Okay, so just substitute the values so that we get the answer delta T. Okay, right. So here the students should be able to understand what is the given data and how far the given data is useful to calculate the required one. Okay, why? Because sometimes superfluous data will be given. Okay, and don't use all the data. Okay, suppose if the question is a very fundamental one, usually all the data is not required. Okay, so sometimes some data will be given, okay, as part of the entire project or program. Okay, right. Next, plasma beam current calculation. Right. A plasma beam delivers a power of 800 watts at a voltage 40 watts. Calculate the beam current in amperes. Right. Power is given 800 watts and voltage is given, okay, 40 watts. Now we have formula power equal to Vi. Okay, power equal to Vi. Okay, right. Here P is given and V is given. We need to calculate I. So I equal to then V by V. So here we have power P and voltage V. Simply substitute these two. So we get beam current I. Okay, right. Here in H factor calculation, a copper sheet is etched using PCM and the depth of the etch is 0.2 millimeters. The lateral edge under the musket is 0.04 mm. Calculate the H factor here. Okay, so depth of HD equal to 0.2 millimeters and undercut equal to 0.04 mm. Okay, and H factor F equal to D by U. Okay, so that we get this one. Okay, now exposure time calculation. Okay, so in PCM process, the photoresist requires an energy dosage of 300 millijoules per centimeter square to fully develop. The UV light source has an intensity of 10 millivolts per centimeter square. Calculate the exposure time required in seconds. Right. So here required energy dosage equal to, we have 300 millijoules per centimeter square. Okay, and light intensity is given, that is 10 milliwatts per centimeter square. Now basically we have formula E equal to I T. Okay, so where energy dosage equal to I, light intensity, and exposure time T. But here we need to find the exposure time T, this one. So this one is known value, this one is known value. So I T equal to E by I. Okay, so this one, substitute the value so that we get time in seconds. Okay, right. Next, etchant volume calculation. Right. PCM process uses ferric chloride at the etchant and takes 5 grams of material to be etched from a brass sheet. The atomic weight of brass is approximately 63.5 gram per mole and the etchant concentration is 1 mole per liter. Calculate the volume of etchant solution consumed. Okay, so here what is the data given? Mass of the brass removed. Okay, so how much? 5 grams. And atomic weight, how much? 63.5 gram per mole. Okay, and the concentration of HNC is 1 mole per liter. Okay, so that is the given data. Now, moles of brass removed, N equal to M by M. M by M. The mass of brass removed by atomic weight. Okay, so that we get in moles. Okay, right. Volume of etchant consumed, V equal to N by C. Why? Because N equal to V into C. So V equal to N by C. So finally we get this value. Okay, so convert into milliliters. So that is 78.7 milliliters. Okay, right. So these are the various problems associated to this. So this is the reference. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.